This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount. Okay, so this lecture is about the concept of the infimum and the supremum, which are concepts that only exist on the real line, so this part won't apply to the several real variables part of this course. So if we took this closed interval here from 2 to 4, we could describe its minimum as 2 and its maximum as 4, because the minimum is just the smallest element of a set which is contained within the set, and the maximum is the largest element of the set contained within the set. And because this is a closed interval, 2 and 4 are both contained within the interval, so they are the minimum and maximum. Here, if we were to have a closed bracket and an open bracket, we could say that 2 is in the interval here, right? This is how we would denote it on the real line. 2 is in the interval, so it's the minimum of the interval. However, there's no maximum because 4 here, this is a strict inequality. So 4 would not be in the set, so we cannot say that there's a maximum. Here, we could say that 4 here is a maximum, but 2 is not a minimum because again, here 2 would not be in the set. And in this case, where it's an open interval, there's no minimum, no maximum. However, we can get more information than just saying there's no min, no max, because there's clearly some sort of bound here, right? No maximum, if we just said that, if we're talking about it, right, and said, this is a set with minimum of 2 and there's no maximum, that might lead us to believe that it could go on to infinity, which is not true. We can see that, for example, 5 isn't in this interval. So we use these concepts here, called the infimum and the supremum, and we can see that would be 2 and 4 for all of these cases. So I'll go on now to define exactly what these mean. We can kind of see why they'd be useful. They kind of describe the bounds of the interval. So if we have A, which is, as I said, of the real line, it's bounded from above if there exists some real number x, such that every element of A is less than or equal to that x. And it's bounded from below if there exists, again, a real number such that for every element of A, x is less than that A. So this x would be an upper bound, this x would be a lower bound. And the supremum of A is just the smallest upper bound of A, and the infimum of A is the greatest lower bound of A. This is called the axiom of completeness. So we take that if A is non-empty and it's bounded from above, then it has a supremum. So this is just an important thing to note, that bounded sets, if they're bounded from above, they'll have a supremum. Then we can get from this, if they're bounded from below, they'll have an infimum. So here we can take some different intervals, and we can see here that different ways to describe these intervals. So here, this interval, open from 0 to infinity, would have no minimum because 0 is not in the interval, no maximum because infinity is not a real number. However, its infimum would be 0. 0 is the greatest lower bound of this interval. And there's no supremum because the set is unbounded from above. It just goes on and on to infinity. Here, this interval, square bracket, -2 up to 3, round bracket. Minimum is -2 because -2 is clearly in its interval. No maximum because 3 is not in the interval. However, its infimum would be -2 and its supremum would be 3 because 3 here would be the least upper bound of A. So, 4, 5, 6, they would all be upper bounds of this interval. But 3 is the smallest one. This interval here, C, minus infinity to 4, well, there's no minimum because minus infinity is not a real number, it just goes on and on forever. No maximum, so maximum is 4 because 4 is in the interval. No infimum, it's unbounded from below, and 4 is also the supremum. So you can see when there's a kind of closed set here, there's an alignment between the maximum and the supremum, and the same here with the minimum and the infimum when we're closed from below. And here we have minus infinity to infinity, just the entire real line. There's no minimum or maximum real number, and there is, again, it's clearly unbounded from below and unbounded from above, so there's no infimum or supremum. So just to kind of put what I hinted at last time into more formality, if A is non-empty and is a set of the real numbers, if its minimum exists, then the minimum and infimum align, they're equal. If maximum exists, then the maximum is equal to the supremum. If the infimum of A exists and the infimum happens to be an element of A, then the minimum is equal to the infimum. And if the supremum exists and that supremum is an element of A, then the maximum is equal to the supremum. Now, if we had B being a non-empty subset of A, which is a subset of the real numbers, if that A was bounded from below, then B would be as well. And its infimum would be greater than or equal to the infimum of A. And similarly, if A was bounded from above, then so would B. And its supremum would be less than or equal to the supremum of A. And you can imagine that kind of easily enough. If we had A as some interval with a lower bound, then B would also have to have the lower bound because it is contained within A, and similar for the upper bounds. Now, from infimums and supremums, you can get a whole load of very nice properties. The first one being the Archimedean property, which says that the natural numbers are unbounded from above, which you probably would have known anyways, but you can prove it this way. And you also get that for any real number, x, there exists some natural number such that x is less than n, or is less than that natural number. So the easy one to think of is that for any negative number, you can just take like 2 or any positive number, and then it's obviously going to be greater than it. Or if x was a positive, then you could take, if you're familiar with computer science, the ceiling function of n. So, you know, if x was pi, you could take 4. If x was, you know, 2,000,000.1, you could take 2,000,000 and 1. You could take 3,000,000. You could take any whole number. And we can do that because n is unbounded from above. If we were to take any non-empty subset, A, of n, then we could find a minimum of A. And that sort of comes back to this idea here, where we have an infimum of n, right? We can bound n from below by 0 or 1, depending on how you count the natural numbers. Some people include 1, some people include 0, some people don't. But we can always find a minimum of A. If A is a subset of the natural numbers, then it's not going to be an interval. It's just going to be a collection of numbers, of like, you know, discrete numbers. You'd be able to list them all, and then you would just choose the smallest one, so a minimum, not necessarily an infimum. Now, now from this we can get the idea of mathematical induction, which is very useful, as I'm sure you've probably seen already. If Pn is any statement which just involves any natural number n, if we have this statement and we can prove it for P of 1. And when we assume that it's true for P of k, where k is a natural number, if from that we can prove that P of k plus 1 is true, then P of n is true. And the way that that kind of works is that, well, okay, if we assumed it was true for P of k, if P of k implies P of k plus 1, so if it being true for one natural number implies the next natural number, then the first natural number we start with is 1. And then if it's true for 1, well then we know, because it's true for when k is 1, then it must be true for when k is 1 here, so that would be P of 2. That's true for when P is 2, P of 2, and then k becomes 2, this becomes 3, and so on. We can go on and cover all of the natural numbers.